Okay, so hi Akansha. Um, let's start with the tutorial. Okay, so welcome to the okay, yeah. So welcome to the week 10 of the problem solving sessions for the discrete maths course. And what we will do today is we will look at some advanced um, methods of counting. So some of them are things that you might have been introduced to in the first week or something, but later on what we try to do is something more advanced. So let's try to let's learn the concepts along as and when we come across the example. So okay, so mostly what we'll do is we'll look into principle of inclusion exclusion, and yeah. So okay, so let's recall that uh, you have this, let's say you have this set A and set B, and this is sitting inside some universe, and we know that A union B complement is same as A complement, or let's say A union B is same as size of A plus size of B minus the size of intersection of the sets. So this is easy to see because what you're doing is you actually want to find the cardinality of the elements in here, and if you simply add the set of elements here and the set of elements here, then you are over counting this set by twice, so that's why you need to subtract that thing. So this is something we also saw in the first week. So this example is warm up for what we're going to see later. So we're going to generalize this. And so the question that is given to you is, you have a basket of 100 apples, and there are yeah, and what you want is you want to eat fresh apples, but the problem is the basket may has several apples that have worms in them, and then there are several that are that have bruises. So um, and you want to sell the fresh ones, that is the ones that do not have worms or that do not have bruises. And using this data, you want to find this count. So can you give it a try? Okay, so let's see. Okay, so what is the value of A union B? Okay, so A union B is simply the set of all the apples that we have. So let's say A here denotes that the apples have worms, and B denotes that they have bruises. But A union B is the total number of apples that we have. So this is total number of apples, and that is given as 100. Then what you know is, you know that there are 20 of them that have worms, and there are 15 of them that have bruises, and additionally you know that there are 10 bruised apples that also have worms. That is, you know that there are 10 apples in here. That is the size of A intersection. Okay, sorry. Oh, okay, sorry. This is not A union B. This is the size of the universe that you have. So this is all the this is all the set of apples that you have. Out of them, these are bad because they have worms, these are bad because they have bruises, and what you are interested in is this area which is outside both of them. So this 100 is basically the size of the universe that you have, and the size of A intersection B is 10. Okay, so okay, so now yeah, so by this you know A union B is same as size of A plus size of B minus size of A intersection B. So this turns out to be 20 plus 15 minus 10, and this is 25. And what you want is you want the yeah, you want the ones that are good, so that is everything that is, so we want A union B whole complement, and this is same as U minus A union B, and that is nothing but 100 minus 25, which is 75. So yeah, so your answer is indeed right. So there are 75 apples here that are, yeah, that are that do not have worms as well as bruises. Okay, good. So now we'll do one example with three sets here. So um, yeah, so you have 350 farmers in a region, so this is the set of all farmers, and you know that um, 260 of them farm beetroot. I'll call this B. Then there are 100 of them that farm carrot. I'll call this C. And then there are 70 of them who farm radish. Okay, and then you have, so what you know is, you know size of universe is 350. You have the number of beetroots farms is 260, number of carrot farms is 100, number of radish farms is 70. Further, what you know is there are 40 that do beetroot and radish, that is, here you know there are 40 elements, so B intersection R is 40. Then C intersection R, that is this region, is 40 again, and this region, that is beetroot and carrot, this is given as 30. So what you want to find is, you want to find the number of farmers that farm beetroot, carrot and radish, all of them. So that is this area in the intersection of all the three sets is what you want to find. So yeah, maybe just yeah, try this out. So okay, this is okay. So let's try this out. So what is the formula that you used? So B union R union C is,
Cardinality of B plus cardinality of C plus cardinality of R minus B intersection R minus C intersection R minus B intersection C plus B intersection C intersection R.
okay, yeah, good. So that is exactly right. So what you did is, you want to find out the total number of elements that are here. So natural thing is, you add the number of beetroot farms, the number of carrot farms and the number of radish farms. So that's what we did here. So but the problem that happened here the is that the elements that are sitting here, in this intersection got added twice, once because of beetroot and once because of carrot, and same thing happens for the other intersections as well. So we counted that twice, but we only wanted to count it once, so we subtracted these quantities. But now what happened is this area in the intersection of all the three sets, this got added thrice for the three sets and got subtracted thrice for the intersections. So what we'll do is we'll add it again. So now that we have this formula, we'll just plug and place the values. So you know this B union R union C is 350, then yeah, B is 260, then 170 minus 40 minus 40 minus 30 plus, so this is the value that you want to find, that is the farmers that farm beetroot, radish as well as carrot. So let me call this X. So yeah, so X is X turns out to be 350 minus 320, which is 30. Okay, so yeah, so that is the idea. So what we did is first we wrote this formula for the union of two sets, then we extended the idea and found out something that can be done to get a formula for the union of three sets. And the general question would be, if you have k sets in general, then how do you write that? So that is something called that is where we use something called PIE. So we'll look into it soon enough. So before that, maybe try this one more example for similar type of problem. So there are 1,000 applicants who for a mountain climbing trip, and 450 of them get altitude sickness. So I'll call this set A. So size of cardinality of A is 450. Then 622 of them are not in a good shape. I'll call this B. So cardinality of B is 622, and 30 of them have allergies. So I'll call this set C. Okay. Now what we want to do is we want to send only those applicants who are good, in the sense they do not have an altitude sickness and they are in a good shape and they do not have any allergies. So that is we are interested in this set that is outside all the three circles. So now you have some additional data. You also know that the number of people who have altitude sickness and are not in a good shape, that is A intersection B. This turns out to be 111. And the number of people who have altitude sickness and allergies, that turns out to be 14. Then there are 18 of them who have allergies as well as have altitude sickness. And additionally, you know that there are 9 of them that lie in this intersection area. So A intersection B intersection C turns out to be 9. And what you are asked to find out is A union B union C complement, because A union B union C would be the set of people who have either of the three problems. Either they have some allergies, or they have altitude sickness, or they're not in a good shape. And we do not want to send any of them. That's why you are actually looking for this area outside. So so maybe try this out. Okay, that was quick. So let's see, let's find out what is A union B union C and like we wrote earlier, this is cardinality of A plus cardinality of B plus cardinality C minus A intersection B minus B intersection C minus A intersection C plus A intersection B intersection C. And if you plug and place the values, this is 450 plus 622 plus 30 minus 111 minus 14 minus 18 plus 9. And yeah, so what is this quantity? So okay, so you have 480 plus 622, this is 1102, and you add 9 into it, so you have 1111, and you are subtracting 111 from that. Then you have 1000 minus 32. So yeah, so this turns out to be 1000 minus 32, and you are interested in the complement of this set. So you are actually interested in A union B union C complement. This is nothing but size of universe minus A union B union C. And we said that initially there are 1000 applicants. That means this total number of people in this rectangle is 1000. So what you do is, this is 1000 minus 32, which is what you have from here, and this turns out to be 32, like you said. Okay, good. So yeah, so now we'll try this another kind of example where okay, so yeah, okay, maybe I'll just state it at this point. So what we did is, you saw this formula for finding the cardinality of union of three sets, and natural thing is you would want to generalize that. If I give you a1 a2 and so on up to ak, and I ask you what is the value of a1 union a2 union ak, then it's not very straightforward, because like you saw, there is a lot of adding and subtraction that goes out. So what you do is, you try the same way. You first add all the sets, then you subtract the pairwise intersection of them, because you had overcounted earlier a2 intersection a3, and you go on like that. Then in this process, what you've done is, you have undercounted the triple intersection. So now what you do is, you add these ones, and you keep on doing that. So finally there will be this one element which will be the intersection of all the sets, and whether you're going to add it or not depends on the value of k. So if k is odd, then you will end up adding it, and if k is even, then you will end up subtracting it. So if I want to write this whole thing in a very succinct form, then yeah, then you can write this as summation of I subset of n I not phi, and yeah, so what this I tells you is, I is a subset of n. So in this case, for example, I is just one element, which is 1. So here I is 1. For example, here I is the set 1 2. So you're just collecting the indices. Here I is 1 2 3. So AI basically denotes the intersection of AI for all I in I. So this is what we mean by that, and you're just interested in this count. And notice that whenever there are odd number of elements in I, you are adding the term. When there are even number of elements in I, then you are subtracting the terms. Therefore the sign is given by -1 to the size of I plus 1. And yeah, that is basically your formula for PIE. This is nothing but your or this is also called pi. So the reason it's called pi is very I mean it's very obvious from what from the way we derived at it. So what we did is you first included all the sums, then you realized you overcounted, then you excluded some terms, then again you realize you have overcounted something, then you add it, and so on. So every time you are approximating your count by adding and subtracting repeatedly. So that's, and hence it gets the name. So what you can do is you can try this principle or the general idea behind it to solve this question. So the question is as follows: you have um, you have this equation x1 plus x2 plus x3 is equal to 13, and you want to find the total number of solutions where x1 x2 x3 take values between 0 and 5. Okay, so let's try to solve this part by part, and I'll just get this question on the other page. Okay, yeah, okay, I think yeah the answer is correct. So let's try to solve this. So um yeah, so what you do is you first ask the question, how many solutions does this equation have, where the only constraint that you have is x1 x2 x3 are all greater than equal to 0. So yeah, so what is the answer for this question if there are no other constraints?
15 choose 2.
Right, so what did you use here to get to 15 choose 2?
Bars and stars method.
Exactly, so you can think of this as there are 13 stars here, and um, you want to make three partitions out of this. So you'll put one partition somewhere here, one partition somewhere here, and the number of stars to the left of the first bar. So this is the value for x1. The number of stars between the two bars is what is x2, and the number of stars here is what is x3. So essentially x1 plus x2 plus x3 is the total number of stars, that is 13, and you want to find uh, three partitions of them. So this is same as distributing. So the number of stars here is 13, and the number of bars here, or yeah, the number of partitions you want here is 3. So Yeah, so the count for this is n plus r minus 1, choose n, and this is nothing but 13 plus 2, choose 13. This is same as 15, choose 2, like Akansha pointed out, and this happens to be 105. Okay, and why did we do this? So okay, so why did we do this? um, we first try to find out all the possible solutions that you can have, and now you don't want all of the solutions. The solutions where um, say for example x1 takes a value of 6, and x2 takes a value of 4, and x3 takes a value of 3. This is bad for us because I have this additional constraint that these x1, x2, x3, they cannot take value of more than 6, more than I mean of at least 6. So these are the solutions that I want to subtract. So these are like bad events for me. So from this um, like do you see how we can use the previous framework? Okay, so what we did is we have the total number of solutions in this box. This happens to be 105, and now there are certain solutions that go bad because um, a is the number of solutions to x1 plus x2 plus x3, which is equal to 13, where x1 is at least 6 and x2 x3 are at least 0. So this is bad for me. All such solutions are bad for me because they violate the fact that x1 should be less than 6. And similarly you can have uh, two other um, two other events where the thing goes wrong because it's symmetric in the sense that it's the same thing, but instead of x1 greater than equal to 6, you have x2 greater than equal to 6, and instead of x2 in the event C, you have that x3 is greater than equal to 6. So these are all the three reasons because of which the solution can go bad, and what we are interested in finding is the area that is outside here. So that is similar to what we were doing all this time. So essentially what we want is we want A union B union C complement, and we know the total number of solutions is 105. Out of that we are going to subtract this A union B union C. So yeah, so we know the formula for A union B union C. We want to find individual the values of individual AIs. We want to find the count for pairwise intersection, and we want to find the count for A intersection B intersection C. So when I say write this, I mean all the symmetric cases that are possible. So that's going to be the general idea. And yeah, so let's try to find out what is the cardinality of A. So A says that this is the total number of solutions to this with this constraint. So what would be the so okay, so what we'll do is we can replace this x1 with a new variable. So you can think of this as 6 plus y1 plus x2 plus x3 is equal to 13, where y1 x2 x3, these are all greater than equal to 0. So why did I do this? I know that x1 is at least 6, so I can think of this as 6 plus something that is non-zero, and that would mean that you are essentially finding the number of solutions for y1 plus x2 plus x3 is equal to 7, where y1 x2 x3 are at least 0. And this is something that we know how to solve. This is something that we did just now. This is nothing but your stars and bars problem now, where n is 7 and r is 3, and we know the answer for this is n plus r minus 1, choose r, choose n, and this happens to be 9, choose 2, and this is 36. Okay, and now what can you say about size of B and size of C? 36, exactly. So B and C are essentially the symmetric cases where instead of x1 you have the constraint on x2. So if you do the same thing by renaming, you'll get the same answer for both of them. So this is also 36 and this is also 36. Now what we want to count is we want to count the event where two elements are banned. That is, you want to find the number of solutions for this where x1 is at least 6 and x2 is at least 6 and x3 is non-zero. So now again we can do the same thing that we did earlier. So what you'll do is, since x1 is at least 6, you can write this as 6 plus y1, and since x2 is at least 6, you can write this as 6 plus y2 plus x3 equals 13, where x1, x3, y1, y2, these are all at least 0. And if you transfer this to the right hand side, you get y1 plus y2 plus y3 is equal to 1, and plus x3 is equal to 1, where y2, y1 and x3, they all are at least 0. And now again this is in the same form that we had earlier, where n is 1, r is 3, and the answer for this would be 3 choose 1, which is 3. And yeah, and now what you are left to find is a1 intersection a2 intersection a3, which is nothing but the set of all solutions where x1, x2, x3, both of them are at least 6. And note that this is not possible, because if all of them are at least 6, then the total sum would be at least 6 into 3, which is 18, and so you can't get 13 at all. So the number of solutions for this is going to be 0. And now what we'll do is, now we have all the values. Okay, I did not mention this here, but again, you know, by symmetry a2 intersection a3 is same as a1 intersection a3, and this is same as 3. So now what we will do is, we will plug and place this into by PIE. We know that the size of A union B union C is same as 3 times size of A plus 3 times size of A intersection B, minus 3 times plus size of A intersection B intersection C. And this is 3 times 36 minus 3 times minus 3 times 3 plus 0, and this is nothing but 3 into 33, which is 99. And yeah, and now you subtract this, so essentially you are interested in finding this, and the total number of solutions for this was 105, and you have A union B union C as 99, so this happens to be 6, like you pointed. So yeah, okay, so your answer is indeed correct. So yeah, 6 is the number of solutions that you can have where x1, x2, x3 are constrained in such a way that they're all non-negative integers that take value less than 6. Okay, so yeah, so if that is clear, try this out, and I'll be back in a couple of minutes. Yeah, hi. Yeah, so if did you if you tried this out, then yeah, do you have any ideas how to proceed, or do you have the solution? Okay, so let's try to formulate this as a polynomial or a multinomial. So right, so there are three different children, C1, C2, C3, and you want to distribute some toys to, you have some 6 toys, and you want to distribute them to the children. Okay, so now the trivial way of doing that, if I don't give you any constraints, then uh, yeah, then what is the total number of ways of doing that? So you just have 6 toys, and there are 3 children, and you want to distribute them, then how many ways can you do that? Right, so notice that the toys are distinct. So this toy is different from, so these are not identical toys, and so this is the keyword. So you have 6 different toys, and therefore um yeah, so therefore for this toy T1, there are 3 ways in which I can distribute it. Either I can give it to C1, C2, or C3. So there are 3 ways in which I can give the toy T1. Then there are 3 ways in which I can independently distribute the toy T3, T2, and so on. So this happens 6 times, and these are independent events. Therefore the total number of ways of distributing um, 6 toys to 3 children is 3 to the 6, like you mentioned. But what the question says is we have an additional constraint that now each child should get at least one toy. So um, yeah, so you can think of this as the um, in terms of sets as follows. So let's say this rectangle represents all the possible ways in which you can distribute the toys, and then let's say this set A is the set of bad sets where there is child C1 who gets more than a toy. Sorry, who does not get any toy. So that is a bad event for us. So you can't distribute it like 0, 4, and 2. So child 1 gets 0, child 2 gets 4, and child 3 gets 2. This is not valid for us because we have an additional constraint that each child should get at least a toy. So from this 3 to the 6 possibilities, we're going to have to remove such bad cases where there is some child who does not get a toy. So A represents the event where child C1 gets 0 toys. And similarly, you can define B2 where child C2 gets 0 toys, and the event C where child C3 gets 0 toys. Okay, so again, like we said earlier, what we're interested in finding is this area that is outside the 3 sets, because that would mean that every child gets at least a toy, and that is exactly what we want to find here. So yeah, we will use the same formula that we have been using so far. So essentially you want to use this. Right, and now what we'll do is we will find out this. So once we get this sum, we will subtract it from this value, and that will give us the shaded area. Okay, so let's find out what is the size of A. So A is the event where C1 gets 0 toys. So how would we go about that? So what is the cardinality of A? Exactly, good. So there are three children, there are six toys. The first toy cannot go to C1 because C1 gets 0. So it can either go to C2 or it can go to C3. So there are two ways of doing this. For the second toy also it cannot go to C1, and then there are two ways of, sorry, there are how many children do, yeah. So you have two ways of doing this. So for each of the toys you have two ways. Therefore this will be 2 into 2 into 2 6 times, and that will give you 2 to the 6. Right, good. And similarly, notice that B and C are also symmetric events, where instead of C1 you will have that C2 does not get any toy. So for the first toy there are two ways of giving, either to give it to C1 or C3. For the second toy also you have same choices, either C1 or C3. So this will also turn out to be 2 to the 6. And same thing happens if you um, yeah, same thing happens if you do it for C3 also. So this is nothing but 2 to the 6. So now that we have this, let us find out the value of A intersection B. So what does that mean? This is the set of all distributions where C1 and C2, that is child 1 and 2, do not get any toy. Okay, so this is what we know. So yeah, so what is the number of ways of doing this? Exactly, there is only one way, because for you have three children here. So for T1 you cannot give it to C1 and C2. You only have to, you're forced to give it to C3. Similarly, for the second toy you can't give it to C1 C2, so you're forced to give it to C3, and this happens for all the toys. So essentially there is only one way, that is give all the toys to the third child. So the number of ways of doing, yeah, so the number of ways of doing this is 1. And similarly you can see that B intersection C and C intersection A is also 1. So this is again by symmetry. Now what we want to find is the third component of our formula, which is A intersection B intersection C. So what does this mean? This is the number of ways of distributing toys where C1, C2, C3, 6 toys each get no toy. So what is the number of ways of doing this? Good. So this happens to be 0, because you have 6 toys and you are not allowed to give it to anybody. So there is no way that you can distribute 6 toys and not give anything to anyone. So this happens to be 0. So now what we will do is we'll plug and place this thing into our formula. So you know A union B union C is 3 times the cardinality of A, which is 2 to the 6, minus 3 times 1 plus 0, and this happens to be so this is 64 minus 3, and this is 192 minus 3, this is 189, and yeah, so this is A union B union C. And what you're going to do is you are actually interested in the size of the set that is outside this. So A union B union C whole complement would be 3 to the 6, which is the total number of ways in which you can distribute without any constraints, minus A union B union C, which is 189. So this is 81 into 9 minus 189. This is 729 minus 189, and that happens to be 540. Okay. Okay, so is this fine, or are there any questions about anything that we have done so far? Okay, good. So, okay, so the other thing that I wanted to say is last time we were, okay, maybe I'll go to the week. Um, yeah, so I remember there was some so what we did last time was we tried to formulate a problem in terms of a polynomial, and then the question was to find a coefficient of something. So yeah, so with one constraint we can okay, so if the constraint is of the following kind, so let me remind you of the problem. So the question is, there are some 4 candidates and you want to distribute 10 votes to them, and the constraint is that each candidate must get at least 2 votes. So then what you did is, we wrote these equations for each of the candidates, and then we multiplied them, and the question was to find the coefficient of x to the 10, because there are 10 votes that we are distributing. So the coefficient will give you exactly the number of ways in which 10 votes can be distributed. Now you have to expand this formula, but we cleverly observed that if you expand this thing and extend it to infinite terms, then yeah, then you can just use this formula. You can approximate it to 1 minus x to the minus 4, and you can use the uh, your binomial theorem and expansion and so on. So that will directly give you the coefficient, because adding more terms is not going to affect your x to the 10. But like you observed last time, if you change the question, and instead of asking at least, okay, yeah, hi Isha. So instead of asking at least 2, if let's say you are asking at most 3, then like you observe, we can't approximate it with 1 minus x to the minus 5, because that will lead to overcounting. This is something we observed last time. And while preparing for the questions for this tutorial, I realized that one way to solve this would be that you use your principle of inclusion exclusion, and that is exactly um, what we have been doing so far. So okay, this example is not really for at most, yeah. So for example, this example that we saw here, you are forcing um, yeah, you're forcing your conditions on the at most side. So then you define your events appropriately, and you can use your PIE to solve this. So for example, here you want to ensure that yeah, yeah, so here you have 12 12 toys that you're going to distribute to 5 children, and um, yeah, so you have 12 action figures. And yeah, in this case, unlike the previous example, the toys were different, but here we did not mention anything, so we are assuming that the 12 action figures are identical. So the number of ways in which you can do this is, you can yeah, so you first find out the total number of ways in which you can distribute 12 action figures to 5 children. Then you think of your bad event as A is the event where, say, the first child gets less than 3 um, gets less than 3 action figures. Then you can define your event B where uh, the second child gets less than 3 action figures, and then you'll have 5 such events because there are 5 children. So you'll have A, B, C, D, E. And yeah, in this case, unlike with 3 sets, you just had a couple of things to calculate, but in this case you'll have to find out A intersection B, then A intersection B intersection C, then the 4 intersections and finally the 5 intersections. And you don't need to find out, for example, B intersection C, C intersection A. Essentially all the 3 choose 2 combinations, or 5 choose 3 combinations, and so on here, because these are symmetric cases. You can see that clearly, that uh, I mean, each of this event is symmetric, where what I mean by A is the child C1 gets less than 3. um, sorry sorry, the bad event would be that the child gets more than 3, and B would be that the child 2 gets at least 4. And this is same as the polynomial equations that we saw. So do you see the connection? So this you can formulate as polynomials. So you can think of this as x1 is the total number of toys that the child 1 gets, x2 is the number of toys that child 2 gets, and so on. So this is 12 because you have 12 number of toys. And we know that x1, x2, and so on up to x5 is at least 0. So this is the condition. This is when you do not impose any constraint. So at the moment I have not imposed any such constraint. Okay, so I'm just calculating the total number of solutions for this, and this we just saw is by stars and bars counting. You know that this is nothing but 12 plus 5 minus 1, choose 12, which is 16, choose 4. So that gives you the uh, yeah, that gives you the total number of elements in this rectangle. Then you further want to find out these sets. So let's say, for example, you want to find out the total number of ways in which child 1 gets at least 4 toys. So this is a bad event for us. So that means x1 you are finding the solution for this, where x1 is at least 4 and x2, x3, x4, x5, these are at least 0. And like we said earlier, what you can do is you can replace this x1 with a new variable y1. So this is 4 plus y1 plus x2 plus x3 plus x4 plus x5 is equal to 12, where x2, y1, x3, x3, x4, x5 is at least 0. And then you can just move this 4 to the left hand side, so this becomes 8. And this is now again the same as this question. So this is again in this form where you have constraints like this and an equation like this. So again, by stars and bars counting, you get your answer to be 8 plus 4, choose 4, which is 12, choose 4. So this is your answer for A, for the event A. Similarly, for B, C, D, E, you get the same. Yeah, for B, C, D, E, you get the same count as 12, choose 4. Then you want to find A intersection B, for example. Then how would you modify this? So how would you modify this equation? Okay, maybe just yeah. So what are the constraints here for A intersection B?
x1 and x2 will be greater than equal to 4 and remaining greater than equal to 0.
Exactly. So this is greater than equal to 0. And then how do you modify this equation with the new variables?
Uh, to x1 we add 4, to x2 we add 4,
Hmm.
and that becomes x1 y1 plus y2 plus x3 plus x4 plus x5 is equals to 4.
4. Exactly. And now all of these variables are essentially greater than equal to 5. So what will greater than equal to 0? So the answer for this would be uh, so what
8 choose
yeah, 8 choose, okay, 4 plus 4 choose 4, which is 8 choose 4. And similarly you can yeah, you can say that B intersection C and all the two intersections happen to be the same value because of symmetry, and you can find out the rest of them and plug and place it into this formula that is given by PIE. So yeah, so I'm just trying to yeah, I just wanted to mention that last time we did not know of any method of solving this and we were stuck there for quite some time. I just want to um, yeah, I just want to remark that this is one way of solving it. There may be another way which is better, but yeah, I just wanted to bring it up. Okay. Okay, so is this fine? So whatever we did in this question as well as the connection to the previous okay, good. So okay. Okay, so yeah, try this out. Maybe yeah, this is also a very nice example of PIE. So yeah, so I'll read out the problem. So there are 10 people who enter a room and they're all wearing a hat, and they while entering the room they give their hats to the servant, and while leaving the servant randomly gives the hat to them. So the question is, in how many ways can the hats be given so that none of the person gets their own correct hat? So yeah, so maybe try this out using the ideas that we saw today so far. So okay, so I see one answer. Yeah, I think Akansha, that is, yeah, I think that is correct. So let's try to solve this step by step. So okay, okay. So so let's simplify the question like we always do. So let's remove all the constraints and ask. So there are 10 people and they are wearing hats, and there are 10 of them, and um, yeah, and what they do is they give their hats to this servant. So now they don't have any hats. Yeah, they don't have any hats, and the servant has this hats h1, h2, and so on up to h10. And what he's doing is he's just um, I mean, they are just distributing these hats to the 10 people in any way that is possible. So in how many ways can this be done? So okay, yeah, so let's answer this first. So in how many ways can you distribute 10 hats to 10 people? So, right, Akansha says this is 10 factorial, which is correct because the first hat can be given to any of the 10 people. Then the second hat cannot go to the person who, so let's say this guy gets the hat h1. Now this guy is out of the question because he can't get any more hat. So now there are 9 people, and the second hat can go to any of the 9 people. So the expression is like this. Once this guy gets the hat h2, then there are only 8 people in question, and so on. This keeps on repeating, and therefore you get this as 10 factorial. So um yeah, so now the question is, we are looking for only certain kind of arrangements out of all these 10 factorial possible arrangements. We are only interested in those where none of the person gets their hat back correctly. So for example, the person 1 gets h2, 2 gets h3, 3 gets h4, and so on. So person 9 gets h10, and maybe the 10th person gets h1. So this is a valid valid arrangement, because if you see, none of the person got back their own hat. But if yeah, if instead this were um, yeah, if instead maybe this guy gets h1 and this guy gets h2, then this is not a valid arrangement because the person 1 gets their own hat. So essentially we want to remove all those arrangements where there is some person who gets back their own hat. So this is similar to the PIE framework, that the principle of inclusion exclusion framework that we have been building. So the first count that we obtained, which is 10 factorial, is the total number of arrangements that are there. Out of this, some are bad. So uh, let's say some are bad because there is at least one person uh, who got uh, yeah, I mean, who got back their own hat. Then let's say there are two people, or okay, there are two people who got their own hat, and so on. So essentially you want to find out, let's say AI is the event. So maybe I'll write it here. So A1 is that person 1 got their own hat back, A2 got their own hat back, then you have 10 events like that. And what you're interested in is this area that is outside all the 10 circles, because that will be everything that is not bad. So essentially you are interested in finding A1 union A2 union and so on up to A10. You're interested in finding this. Once you get this quantity, you will subtract it from 10 factorial. So once you get this quantity, you subtract it from the total number of possible arrangements, and that will give you the desired area that is outside the circles. So our goal now is to find this. And how do we do that? we already know this principle of inclusion exclusion, and we know a very succinct way of writing it. So we know that union of AI is same as summation of minus 1 to the r, okay, maybe minus 1 to the size of I plus 1. I is a subset of v, is a subset of n, which is non-empty, and the size of AI. So where, what do I mean by AI? AI is the intersection of all the events that are in I. So for example, A of I, where I is 2 3 4, would mean A2 intersection A3 intersection A4. And what does that mean? This means A2 means that person 2 does not get their own hat, person 3 does not get their own hat, and person 4 does not get their own hat. So all such arrangements will be included in this set AI, where I is given by this. So that is basically what we mean by this. So this is something that we saw earlier today. And notice that in all the examples that we saw, maybe like previous 2-3 examples, notice that I did not calculate, for example, yeah, here we only calculated A intersection B, and then I said B intersection C, C intersection A, these are going to be the same because they are symmetric. They only depend on the size of the set. Similarly, here also we only calculated A, the size of A. We said that the size of B and C will be same because again the case is symmetric. So in this case also, what happens is, it does not matter what subset of people I'm choosing. As long as I'm choosing a subset of people that is of size R, my answer is going to remain the same. So I don't have to go on calculating AI for every subset. So I can rewrite this as summation of R from 1 to n minus 1 to the R plus 1, and I can go over all the subsets of n which are of size R, and then I can add this AI. So is this thing fine? So how did we get from here to here? Is this fine? Okay, good. And how can I simplify this further? So what is this? How many such summations will be there? So you're looking for R sized subsets of n, that is, you're choosing R elements from n. How many ways can you do that?
N choose R.
Exactly. So this is n choose R times size of AI. So now the only thing that we need to do is find out what is this size of AI. And yeah, so let's find that out. So our goal now is to find out the size of AI. And what do I mean by AI? AI means for all I in AI does gets their own hat. And in how many ways can we do that? Okay, so maybe even before we answer that, let's answer a very a simpler question. So let's say I want to find out the cardinality of A1. So A1 means person 1 gets their own hat. So what does that mean? So here you have P1, P2 and so on up to P10, and you know that the first person gets the hat H1. For the remaining people, we don't know how they're going to get hats. They may or may not get their own hats. So that is for the hat 2 there are 9 choices here. For the hat 3 there are 8 choices. For third hat 7 and so on. So this is nothing but 9 factorial. Is this fine? Okay, good. So similarly, what can you say about A1 intersection A2? So this is number of ways P1 and P2 get their own hat.
Eight factorial ways.
Exactly. Good. So A1 gets P1 gets their own hat, which is H1. P2 gets their own hat, which is H2. Now for the remaining 8 hats, H3 to H10, you're going to distribute it to P3 to P10 in any order. So first hat can go to any of the 8 people, second can go to any of the 7 people and so on. So this turns out to be 8 factorial. So in general, what is the value of A1 intersection A2 intersection up to AR?
10 minus r factorial.
Exactly. So this will be 10 minus r factorial, because for the r people you have already given their own hat, so they are out of the question. For the remaining n minus r people, you can distribute in 10 minus r factorial ways. So that is exactly what we were asking for here. So ai, if the size of I is r, then this is nothing but n minus r factorial. And now that we have this answer, we will plug and place this into the equation that we had here. So what you have is union of ai, I is from 1 to n, is summation of r from 1 to n minus 1 to the r plus 1, and n choose r, size of ai, which we are going to replace with n minus r factorial. And now this is r is 1 to n minus 1 to the r, n factorial. I'm just expanding the the formula for n choose r. This is r factorial n minus r factorial times n minus r factorial. And now this term nicely cancels out, and what you get is, so this n factorial is independent of r here, so I can push this away, I can push this out. So this is n factorial times summation r is 1 to n minus 1 to the r plus 1 1 over r factorial. And notice that what we calculated here is the set of is this area, that is, I mean the number of ways that is inside this set. And what we wanted really is what is outside this set, so we're going to subtract it from 10 factorial, which is the total number of ways in which you could have arranged. So the answer that we want, or that is number of ways of distributing 10 hats to 10 people, so that get their own hat, is same as n factorial minus n factorial times the expression that we had here, summation r is from 1 to n minus 1 to the r 1 over r factorial. And what I'll do is I'll push this term inside this summation. So what I'll do is I'll write this as follows. I'll write this as n factorial times summation of r is from 0 to n minus 1 to the r 1 over r factorial. So notice that these two are essentially the same terms, because when I substitute r to be 0, then this entire term becomes 1, and that gives you this n factorial outside. And for r is from 1 to n, you exactly get this equation. So this is just a succinct way of writing this. And notice that yeah, e to the minus 1 um, is same as 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, okay, alternatingly, minus plus and so on, minus 1 over 4 factorial and so on. And this is exactly what we have over here. So I can replace this with n factorial over e, and this is not exact count, this is an approximate count, because here you are cutting it off at um, you're cutting off the alternate addition subtraction at n, but here I'm going at infinity, so I'm getting something that is approximately this. But yeah, in general, this is what you would get. And n for us, for our case, we were talking about 10 people, so n for us is 10. Therefore the answer to this would be 10 factorial over e. So this kind of arrangement where you're talking about distributing something among people such that nobody gets their own thing, this is what is called derangement. So this is called derangements in mathematics and combinatorics, and this is a very well studied problem, and you can find its applications everywhere. And yeah, so that is what I wanted to convey in this problem. But if there are any questions about anything that we did so far, then please feel free to ask. I'll wait for some time so you can stare at it. Is this fine, or is there any part that you you want me to repeat, or if you have any questions, then please feel free to ask. Okay, so is this fine? Shall we move on to the next question? Okay, so I'll move on to the next one. So the next question is that you have a group of people who have come to a picnic. So there are 7 groups. There's a group of there are 7 groups, and they've brought their own lunchbox. So there are 7 lunch boxes. There are 7 groups, and what happens is they just yeah. So they've just collected all of their boxes at some place, and while coming back, they got the lunch boxes got randomly distributed to them. So what we want to find out is what is the total number of ways in which the lunch boxes can be exchanged amongst them, so that none of them get their own box. So this is similar to what we did earlier. So you can tell me if you have any thoughts similar to that, or if you have any approach. I'll maybe give you some time to think, and then please let me know what you think about the approach. Okay, is the question clear, or do you yeah, do you want me to explain some part of it? Okay, so let's maybe yeah, let's try to solve this together. So let's say there are seven groups, and the groups is G1, G2, G up to G7, and um there are seven lunch boxes, L1, L2 up to L7. So what is the total number of ways in which we can distribute seven lunch boxes to seven groups? So this is nothing but 7 factorial, because first lunch box can go to any of the 7 people, second one can go to the remaining any of the 6 remaining people, and so on. And again, this is your classical, like you can formulate this in terms of a derangement problem, where where AI is the event that group GI gets their own lunchbox. And similarly, you can define AI to be the event where for all groups I in I, GI in I, or for all I in I, GI gets their own lunchbox. And what you will do is you will again use the by PIE. We know that the union of I is 1 to n, is summation of R is 1 to n minus 1 to the R plus 1 times n choose R times AI. Okay, and this n choose and again you are left to finding this AI, which again happens to be n minus R factorial, for the same reason that um, if you want to find a1, then a1 gets l1, and for the remaining 6 people you can distribute in 6 factorial ways. So again this turns out to be summation R is 1 to n minus 1 to the R plus 1 n choose R n minus R factorial, and this n minus R factorial cancels out, and you are left with n factorial by R factorial. So essentially the answer that you are looking for will be n factorial minus this term here, and that happens to be n factorial by E. This is approximately, and n for us here is 7, so the answer for us would be approximately 7 factorial over E. So I am not doing everything step by step, because this is exactly what we did in the previous example. So it's just about understanding how to define your sets AI, and understanding what derangement is in play, and then just using the formula that we derived earlier and putting it into this. So essentially, if you are looking for the derangement number, then that is n factorial over E. You can directly say this without going through all the steps. um, yeah, but as long as you're sure that it's a derangement problem, so which it is in this case. So this is your derangement problem, and that's your answer. So are there any questions about what we did, or do you want to expand any step? Then please let me know. Okay, so assuming this is fine, I'll move on to the next question. And yeah, so maybe there are so maybe try this out. So again, this is a similar derangement problem, and I just want you to identify the derangement that is in play. So the question here is as follows: there's a postman, and he can put 12 letters into respective envelopes. And okay, so I'll maybe draw this. So there are 12 envelopes here, E1, E2, and so on up to E12. Now there are also 12 letters. So this is L1, L2, and so on up to L12. So ideally what he wanted to do is he wanted to put L1 into E1, L2 into E2, L12 into E12. But there is some mixing that happened, and now this is randomly going to put the letters into the envelopes. Okay, and the question that we want to find, the answer that we want to find out is, in how many ways can you do this so that exactly 5 of them go into the into the correct envelope. So for example, it could be that L1 goes to E1, L2 goes to E2, and so on up to L5 goes to E5. But after that point, from E6 to E12, none of the letters goes into the right place. So how do we so how do we find this out? So this is slightly different from derangement. So maybe just give it a try and you can tell me your ideas or your answers. Also, if there is any part that you want me to clarify at any point, then please let me know. Okay, so any ideas or any starting points or thoughts that you have that you would like to share? Okay, so let's try this out. So so what we'll do is, uh, you can't directly use the derangement here, but so what we'll do is we'll modify this question slightly. Okay, so what you do is, you know that there are exactly 5 letters that go into the correct envelopes, and those could be any 5 of this 12. So the first question is, in how many ways can you choose? Five envelopes such that they yeah, they get the right letter. That is, yeah, so in, yeah, so that is given by, so what is this, what is the answer for this question 1? So there are 12 envelopes and you want to choose 5 of them. So in how many ways can we do that? So this is nothing but 12 choose 5. It is not permutations but combinations, because it does not matter what order, what is the order in which we are choosing the envelopes. As long as I have 5 envelopes, I'm fine with it. So what you do is, you give me from this 12 set of envelopes, you give me a set of 5 that I know they're going to get their own respective letters. And for the remaining 7, what I know for sure is none of them get their own letter. And what do we mean by that? This is exactly same as finding the derangements, number of derangements for n equals 7. And what do we know from the previous examples, the 2-3 examples that we saw? We know the answer for this is n factorial over e, which in this case is 7 factorial over e. So the total number of ways in which you can do that is, first you choose your, is you'll just multiply both the answers. First you choose your 5 envelopes. That can be done in 12 choose 5 ways. And once you've done with that, for the remaining 7 envelopes, you are just counting the number of derangements. So this is given by 7 factorial over e, and if you multiply this will turn out to be 12 factorial over 5 factorial into 7 factorial. By 7 factorial into e, this cancels out, so this is 12 factorial over 5 factorial times e. So I won't multiply this, but yeah, this is essentially, you can if you want, you can expand this out and see for yourself what answer you get. But yeah, but is the general idea clear about how we converted this into a derangement problem? Okay, so is this fine, or are there any questions about this? If there is, you can ask me. Yeah, you can interrupt me now. Okay, so good. So we'll solve this final example for the today's session. Um, okay, so let me read this out. So there's a school that organizes a game where there are 100 students, and they are grouped into sets of 50 each. So you're going to form two groups, G1 and G2, where the number of students are going to be divided as 50-50. And for each group, the people here are going to be assigned with number 1, 2, 3, and so on up to 50. Similarly, for the other group also, they are going to be assigned numbers 1, 2, 3, and so on up to 50. Okay, now yeah, yeah, so now what happens is, they're going to club themselves together into pairs of two. So once the game starts, they're going to find their partners. So you want to find the, so maybe a 3 from here can be partner, a partner of a 1 from here, or can be a partner of a 3 from here. So essentially you're going to pick one person from here, one person from here, and they're going to form a team. So yeah, so what you do is, you want to find out the total number of ways in which the game can end, where there are exactly 25 people who are matched to their own partners, I mean the same numbered partners. So maybe 1 here is mapped to 1, so one possibility is 1 here is mapped to 1 here, 2 here, and so on up to 25 is mapped to 25 from the group G1 and G2. And for the rest of them, they don't get, none of them gets their own numbered partner. So in how many ways can you do this? Okay, so yeah, so let's try to solve this like similar to what we did earlier. You know that 25 of them are going to be correct pairs. So the question is which 25 of them are for which 25 this is going to happen. So there are 50 numbers. Out of them we are going to choose 25 which are going to be correctly mapped. So it could be any set. It could be say 25, 26, 27 and so on up to 50 and so on. It could be it could be any such set, but yeah, we're just looking for in how many ways can you find such a set. Now for the remaining 25 students, you know that none of them gets their own partner, so this is same as derangement. So first is choosing 25 numbers which get for which they get correct partners, and then this is the number of derangements, the number of ways you can uh, yeah you can I mean yeah, you can find the derangements among the remaining 25 people so that none of them gets their own partner. So this is number of derangements. And again, if you expand this further, you get 50 factorial over 25 factorial times c. And I'm not going to find this answer exactly right now, but but I hope the example demonstrates how to use how to use derangements to solve questions of this kind. So yeah, are there any questions about anything that we discussed today? Then feel free to ask. um, Otherwise, next we will meet on the upcoming Friday, same time, 6 p.m. to 8 p.m. Okay. Okay, good. Thank you for attending. Okay, have a nice day.